In this lesson, we will learn about exponential and logarithmic functions, evaluating and graphing exponential and logarithmic functions, and solving exponential and logarithmic equations. We will go over some properties of exponents and logs, and expand and condense logs, and then we will go over some transformations of exponential functions and writing equations of exponential and logarithmic functions given their graphs. An exponential function is a function of the form b to the x, where b is a positive real number not equal to 1. Here's an example of an exponential function. Let's evaluate this function for x values between -4 and 4 and then plot them on a grid to see the behavior of the function. F of -4 is 1/16. F of -3 is 1/8. F of -2 is a quarter. F of -1 is a half. F of 0 is 1. F of 1 is 2. F of 2 is 4. F of 3 is 8. And f of 4 is 16. We can see that the function increases exponentially as x values increase. Interestingly, the function is never 0 or negative, so there is a horizontal asymptote at y equals 0. Drawing a curve through the points, we will have the graph of f of x equals 2 to the x with a horizontal asymptote of y equals 0. Here's an exponential function 2 to the x minus 1 power plus 3. To evaluate f of -1, we simply plug -1 into x and get 2 to the -2 power plus 3. This can be written as 1 over 2 squared plus 3, which is 1/4 plus 3 and simplifies to 13/4. Similarly, to evaluate f of 1, we plug 1 into x and get 2 to the 0 plus 3, which simplifies to 4. Following the same process, we can evaluate f of 3 to get 7. Exponential functions have no domain restrictions, and so the domain of this function is all real numbers. And the range of f of x is 3 to infinity. This is because as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, 2 to the x minus 1 approaches 0, and 2 to the x minus 1 plus 3 approaches 3. And so there is a horizontal asymptote at y equals 3. F of -1 equals 13/4, f of 1 is 4, and f of 3 is 7. Plotting these points and drawing the horizontal asymptote, we can draw a curve through the points to graph the exponential function. Here's another example. We evaluate the function at 3 different values to find 3 points. Then we find the domain and range, and then the horizontal asymptote, and then graph it. Since the exponent is x plus 2, we will choose x equals -2 as one of the points, and then 1 point to the left and 1 point to the right of it. That is, we will evaluate the function at -3, -2, and -1. F of -3 is 1/3 to the power of -3 plus 2 and then minus 1. -3 plus 2 is -1, and raising 1/3 to the -1 is the same thing as raising the reciprocal of 1/3 to +1. So we get 3 to the first power minus 1, which simplifies to 2. Following the same process, we evaluate f of -2 and f of -1. Because exponential functions have no domain restrictions, the domain of f of x is all real numbers. The range of the parent function of an exponential function is 0 to infinity, and because of -1 at the end of f of x, all values of the function are subtracted by 1, so the range of the function is -1 to infinity. We can now plot the 3 points we have found. Based on the range of the function, there is a horizontal asymptote at y equals -1, so we draw a dashed line at y equals -1, and then we draw a curve through the points to graph the exponential function. A logarithmic function is a function of the form f of x equals log base b of x, where b is a positive real number not equal to 1 and x is a positive real number. Let's look at y equals log base b of x. What this means is that some base b raised to the power y is equal to x. So in a sense, logarithmic functions are another way to represent an exponential function where the input x and the output y are swapped. Here's an example: f of x equals log base 2 of x. We can convert this into an exponential function 2 to the f of x equals x. We don't want to always do this, but for now, it will help us better understand it. To evaluate f of negative 1, we simply replace x with negative 1. We ask ourselves, 2 to what power is negative 1? We can see that there is no such a real number where this is possible. So f of negative 1 is undefined. F of 0 is log base 2 of 0. We ask ourselves, 2 to what power is 0? Again, there is no such a real number where this is possible. So f of 0 is undefined. Recall that the domain restriction of logarithmic functions is that input must be positive, not 0 and not negative. F of 1 is log base 2 of 1. We ask ourselves, 2 to what power is 1? We know that anything to the 0 power is 1, so f of 1 is 0. F of 2 is log base 2 of 2. We ask, 2 to what power is 2? And that is 1, so f of 2 is 1. Now, I would not try 3. It is best to strategically choose numbers that I am able to evaluate. Since the base of this log is 2, I will only choose inputs that are powers of 2. So my next input instead of 3 will be 4. So f of 4 is log base 2 of 4. We ask, 2 to what power is 4? So f of 4 is 2. And my next input for this log would be 8 because I know 2 cubed is 8. So f of 8 is log base 2 of 8, which I know is 3 since I strategically chose the input. So f of 8 is 3. We have 4 points for this function. Let's find the domain and range and then try to sketch the graph of it. We know that logarithmic functions have domain restrictions that they can only take positive x values. So the domain is 0 to infinity. However, they have no restrictions on their output, so the range is all real numbers. We now plot the points. However, this is not enough to draw the graph. We know that the domain is 0 to infinity, and so, like exponential functions, the logarithmic functions have an asymptote too. The difference is that exponential functions have a horizontal asymptote, while the logarithmic functions have a vertical asymptote. Because there is a limit of 0 on the lower end of the domain, the vertical asymptote is at x equals 0. So we draw a dashed vertical line at x equals 0, and now we can draw a curve through the points to graph the function. Here's another example. We know that the input of logs must be positive, so we will choose x values that will make x minus 2 positive. F of 3 is log base 3 of 3 minus 2, then plus 1. 3 minus 2 is 1, and log base 3 of 1 is 0, so f of 3 is 1. We will choose 5 as the next input because 5 minus 2 is 3, and 3 is a power of 3. So f of 5 is log base 3 of 5 minus 2, then plus 1, that is, log base 3 of 3 plus 1, which is just 1 plus 1, which equals 2. So f of 5 is 2. For the next input, we want x minus 2 to be the next power of 3, that is 3 squared. So we look for x value that makes x minus 2 equal to 9, which is x equals 11. So we evaluate f of 11 next. Log base 3 of 11 minus 2, then plus 1 can be written as log base 3 of 9 plus 1, which equals to 2 plus 1. So f of 11 is 3. Domain of f of x is all real numbers greater than 2, that is, 2 to infinity. And the range of f of x is all real numbers since logarithmic functions have no restrictions on their range. Vertical asymptote is at x equals 2. Now that we have all the information we need, we can graph the function. We plot the 3 points we have, then draw the vertical asymptote, and then draw a curve through the points to graph the function. We can generalize a formula for exponential functions. any exponential function can be written as f of x equal to a times a base b raised to the power c times x minus h and then plus k. Recall that the base b must be a positive real number not equal to 1. Domain of exponential functions is all real numbers. Now, if a is positive, the exponential function has a range of real numbers greater than k, and therefore, since the range can never be k, there is a horizontal asymptote at y equals k. If a is negative, the exponential function has a range of real numbers less than k, and the horizontal asymptote at y equals k. We can see that the only thing different between these cases is the range. That is because a negative value of a results in a reflection into the x-axis that only changes y values. Similarly, we can generalize a formula to represent any logarithmic function. Note that the base is b, same as the base of exponential functions. A is the vertical stretch similar to the exponential functions. The exponent of the exponential function is the input of the logarithmic function, and k is the vertical translation just like the exponential functions. Again, we have two cases, but this time, the sign of c determines the direction of the graph. So if c is positive, domain is real numbers greater than h, and if c is negative, domain is real numbers less than h. The range of all logarithmic functions is all real numbers, and they have a vertical asymptote at x equals h. Note that in logarithmic functions, the domain would change based on the sign of c as the direction of the graph changes. Now that we have explored both exponential and logarithmic functions, let's look at some of their properties. Given two different bases x and y, x to the m times y to the m can be expressed as the quantity xy to the m power. For example, 5 cubed times 7 cubed can be written as 35 cubed. X to the m times another expression with the same base x to the n can be expressed as x to the quantity m plus n. For example, 5 cubed times 5 to the 4th can be written as 5 to the 7th. If two expressions with the same base to some exponents are divided, like x to the m divided by x to the n, the division can be expressed as x to the quantity m minus n. For example, 5 cubed divided by 5 to the 4th can be written as 5 to the negative first power. X raised to a negative exponent like x to the negative m can be expressed as 1 over x to the m. For example, 5 to the negative third can be written as 1 over 5 cubed. And so we can simplify the expression in the previous example to 1/5. We know that anything raised to the 0 power is 1, so x to the 0 equals 1. For example, 5 to the 0 equals 1. Anything raised to the first power is itself, so 5 to the first is just 5. Following the properties of exponents, we can arrive at some of the properties of logarithms. Log base b of x to the n can be expressed as n times log base b of x. This is called the power rule of logs. For example, log base 3 of 5 squared can be written as 2 times log base 3 of 5. Log base b of the product of x and y can be expressed as log base b of x plus log base b of y. This is called the product rule of logs. For example, log base 3 of 5 times 7 can be written as log base 3 of 5 plus log base 3 of 7. Log base b of the quotient of x and y can be expressed as log base b of x minus log base b of y. This is called the quotient rule of logs. For example, log base 3 of 5/7 can be written as log base 3 of 5 minus log base 3 of 7. Log base b of 1 is 0. This is because any base b to only 0 would equal 1. For instance, log base 3 of 1 is 0 because 3 to the 0 would equal 1. And log base b of b equals 1 because b to the first power would equal itself. So log base 3 of 3 would equal 1. Now, log base b of b to the x can be expressed as just x. We can apply the power rule of logs and get x log base b of b, and we know that log base b of b equals 1, so this simplifies to just x. So log base 3 of 3 to the 5th is just 5. These were some properties of logs. There is an irrational number e, approximately 2.718, that is called the natural base. And so, if the base of a log is e, instead of saying log base e of x, we say natural log of x, and denote it by ln. There is also a common base 10. That is, instead of writing log base 10 of x, we just write log of x. We can change the base of logs to make simplifying expressions easier or express answers in different bases. The change of base formula of logs says that log base b of x can be expressed as log base c of x over log base c of b, where c can be any positive real number not equal to 1. Following the properties of logs, we can express all of these properties in terms of natural logs. Remember that for a natural log, the base b is simply the natural number e. So the power rule of logs can be modified to natural log of x to the n equal n times natural log of x. The product rule of logs can be modified to natural log of xy equals natural log of x plus natural log of y. The quotient rule of logs can be modified to natural log of x divided by y equal to natural log of x minus natural log of y. Natural log of 1 is simply equal to 0. Natural log of e equals 1. And natural log of e to the x simplifies to just x. Using properties of logs, we can expand a logarithmic expression. Here's a trick to use in expanding this logarithmic expression. X cubed is in the numerator of the input of log. We use this as an input of a positive log. Y to the 5th is also in the numerator of the input of the log. So we use this as the input of another positive log. Z is in the denominator of the input of log. We use this as the input of a negative log. And square root of x minus 1 is also in the denominator of the input of log. And we use this as the input of another negative log. Note that all of the logs have the same base as the base of the original log. Now we can apply the power rule of logs when appropriate. So we get 3 log base 2 of x plus 5 log base 2 of y minus log base 2 of z minus log base 2 of quantity x minus 1 to the 1/2 power. Note that we need to express the radical as a rational exponent so we can apply the power rule of logs. The first 3 terms remain unchanged while the last term becomes negative 1/2 log base 2 of the quantity x minus 1. We can also condense logarithmic expressions using properties of logs. We first apply the power rule of logs whenever applicable. So we get natural log of x squared minus natural log of y cubed plus natural log of cube root of z minus natural log of quantity of x minus 1. And then the input of any positive log goes to the numerator of the input of the condensed log, and the input of any negative log goes to the denominator of the input of the condensed log. So we get natural log of x squared cube root of z in the numerator, because they were inputs of positive logs, over y cubed times x minus 1 in the denominator, because they were inputs of negative logs. In this section, we want to focus on solving exponential or logarithmic equations. Here's an example of an exponential equation. One way to solve exponential equations is to match the bases. In this case, the bases are the same, and so the only way the two sides are equal to each other is if the exponents are the same. So we set the exponents equal to each other and go through the solving algorithm to solve for the variable and get x equal to negative 4. Note that the exponential functions have no domain restrictions and have a domain of all real numbers, and so it is okay for x to be any real number, and so x equals negative 4. Here's another example of an exponential equation. We want to match the bases if possible. We must never multiply or divide the bases by any number. However, we can rewrite the base using another expression. For instance, 4 can be written as 2 squared, and 1/8 can be written as 2 to the negative third power. We know that raising a base to a power and then to another power can be expressed as the base raised to the product of powers. Now that we have matched the bases, the only way the two sides of the equations are equal to each other is if the exponents are the same. So we set the exponents equal to each other and go through the process of solving for the variable and get x equal to -3. Because exponential functions have no domain restrictions, x is allowed to be any real number, so x equals -3. Here is another example of an exponential equation. We first try to match the bases. However, we can see that there is no way to express 3 and 10 as a base to another nice power where the bases match. So we need to use a different technique. In this technique, we simply take log of both sides. The goal is to expand these logarithmic expressions to get simpler expressions. We first apply power rule of logs and get x plus 2 times log of 3 equal to x minus 1 times log of 10. On the left side of the equation, we distribute log of 3 into x plus 2 and get x log of 3 plus 2 log of 3. And on the right side of the equation, we know that log of 10 simplifies to just 1, so we write the right side as just x minus 1. To solve for x, we want all occurrences of x to be on the same side, and everything else on the other side. So we subtract x plus 2 log of 3 from both sides to get this equation. Now, to solve for x, we want only one occurrence of the variable. Since both terms on the left side have x, we can factor out the x and get x times log of 3 minus 1 equal to -1 minus 2 log of 3. And to solve for x, we simply divide both sides by log of 3 minus 1. Again, there is no domain restrictions for exponential functions, so x equals -1 minus 2 log of 3 all divided by log of 3 minus 1. Though we have solved the equation and have an answer for it, we can simplify the answer or find other forms of the same answer in exact form. Since all of the logs of this answer have a base of 10, we can write 1 as log base 10 of 10 and apply power rule of logs and rewrite 2 log of 3 as log of 3 squared and get this expression as another form of the answer. We can see that both expressions in the numerator are negative, so we can factor out a negative from the numerator. We can also condense the numerator and the denominator using the product and quotient rule of logs and simplify the inputs and get another form of the exact answer. And if we apply the change of base formula, we can express the answer as one single log. It is arguable as to which of these forms are more simplified, but we can play around with the properties and get different forms of the solution to this equation. Here's another example of a logarithmic equation. We can convert the logarithmic equation to its exponential form and rewrite it as 3 to the 5th equal to x minus 1. Raising 3 to the 5th, we get 243 equal to x minus 1, and adding 1 to both sides, we can solve for x and get x equals 244. Note that, unlike exponential functions, logarithmic functions have domain restrictions, so we need to check to see if this answer is acceptable. We plug 244 into the original equation and get log base 3 of 243 equal to 5, which in fact is true. So we can say x equals 244. Here's another logarithmic equation. The only way log base 3 of x minus 1 equals log base 3 of 2x plus 1 is if x minus 1 equals 2x plus 1. We go through the solving process and solve for x and get x equals -2. We need to make sure this answer does not violate any domain restrictions. X minus 1 must be positive for log base 3 of x minus 1, and 2x plus 1 must be positive for log base 3 of 2x plus 1. That is, x must be greater than 1 and x must be greater than -1/2. The portion that satisfies both of these logs is 1 to infinity, And since negative 2 is outside of this interval, it is an extraneous solution, and there is no real solution to this equation. Here's another example of a logarithmic equation. Note that the two logs have different bases. We can use the change of base formula to rewrite log base 9 of x plus 3 as log base 3 of x plus 3 over log base 3 of 9. Log base 3 of 9 equals 2, so we can simplify the right side. We then multiply both sides by 2 to get rid of the 2 in the denominator. Using power rule of logs, we can make 2 an exponent of x plus 1. Now that we have logs of the same bases, the only way these two sides are equal to each other is if the inputs of logs are the same. That is, if x plus 1 squared equals x plus 3. We FOIL the left side and get x squared plus 2x plus 1, which needs to be equal to x plus 3. Moving everything to the left side and setting it equal to 0, we can see that the left side factors to x plus 2 times x minus 1. So either x equals negative 2 or x equals 1. We need to ensure that they don't violate any domain restrictions. For the left side of the original equation, x plus 1 has to be positive, and for the right side of the original equation, x plus 3 has to be positive. That is, x has to be greater than negative 1 and greater than negative 3. The portion that satisfies these conditions is real numbers greater than negative 1. Since negative 2 is outside of this interval, x equals negative 2 is an extraneous solution. And because 1 is within the acceptable interval, x equals 1 is an actual solution. We have already gone through graphing exponential and logarithmic functions. Let's look at transformation of graph of exponential and logarithmic functions. There are both horizontal and vertical transformations. The value of h translates the graph horizontally, left or right. That is because h affects the input and changes x values. The value of c stretches the graph horizontally by a factor of 1 over c. Because c affects the input, it stretches x values. And a negative value of c results in a horizontal reflection, a reflection into y-axis. The value of k translates the graph vertically up or down, that is because k affects the output and changes y values. The value of a stretches the graph vertically by a factor of a. Because a affects the output, it stretches the y values. While the negative value of a results in a vertical reflection, a reflection into x-axis. Let's explore transformations on an exponential function. Here's a graph of an exponential function, f of x equals 2 to the x. The transformed function g of x equal 2 to the x minus 1 is the graph of f of x shifted right 1 unit. The transformed function g of x equals 2 to the x plus 1 is the graph of f of x shifted left 1 unit. The transformed function g of x equals 2 to the 2x is the graph of f of x stretched horizontally by a factor of 1/2. It looks narrower. The transformed function g of x equals 2 to the 1/2 x is the graph of f of x stretched horizontally by a factor of 2. It looks wider. The transformed function g of x equals 2 to the negative x is the graph of f of x reflected into the y-axis. The transformed function g of x equals 2 to the x plus 1 is the graph of f of x shifted up 1 unit. The transformed function g of x equals 2 to the x minus 1 is the graph of f of x shifted down 1 unit. The transformed function g of x equals 2 times 2 to the x is the graph of f of x stretched vertically by a factor of 2. It looks taller. The transformed function g of x equals 1/2 2 to the x is the graph of f of x stretched vertically by a factor of 1/2. It looks shorter. What if we were asked to find the equation of an exponential or logarithmic function given a graph? Here's an example. We can identify this graph as an exponential function. The horizontal asymptote is at y equals 1, so the value of k is 1. The horizontal translation is 3 units right, so the value of h is 3. We plug in these two values of h and k and simplify the equation, and we get a equals 1. Now that we have the value of a, h, and k, we just need to find the base b. Using the point 4, 6 from the graph and the values of a, h, and k, we get this equation. Solving for b, we get b equals 5. And putting all of these values in the transformed equation, we get f of x equals 5 to the x minus 3 power plus 1. Here's another example where we're asked to find the equation of the function for the given graph. We can identify this graph as a logarithmic function since it has a vertical asymptote. The vertical asymptote is at x equals -1, so h is -1. We can see that there is a vertical translation 2 units up, so k equals 2. Putting these two values into the equation, we can simplify the equation to 1 equal a times log base b of 9. Using the power rule of logs, we get log base b of 9 to the a equals 1. And converting it to the exponential form, we get b to the first equals 9 to the a. We can see that if b equals 3 and a equals 1/2, this equation would be true. So perhaps b equals 3 and a equals 1/2. Using these four values and putting them into the transformed equation and simplifying it, we get f of x equals 1/2 log base 3 of the quantity x plus 1, then plus 2. Let's make sure we have found the correct equation for the function. We evaluate the function at x equals 0 to ensure that the function goes through the point 0, 2, and we see that, in fact, f of 0 is 2. We go through the same process to see if the equation we have found satisfies the other points, and see that, in fact, f of 2 equals 2.5 and f of 8 equals 3. So the function we have found is in fact the correct function.